Good morning.
Good morning. Good morning.
So let's see, is Jordan there?
I think she went to the bathroom. I don't know. She was here last hour, so she should be.
Okay. All right. Let's see, is everybody there in Winslow?
Yeah, everyone's here.
All right. And then in Joseph City, where are the boys?
They had a baseball game today.
Oh, okay. All right. Oh, shoot. All right. I just messed up. Okay. So we said everybody was in Winslow and baseball gone. All right. So, and Jordan is there. Okay, wonderful. All right, so today the plan is we're gonna again go just kind of review the stuff that you did without me in 8.5 and 8.6. So just kind of be a review of what Mr. Fritz went over. So, but any questions, comments, concerns before we get started? All right, so we're gonna kind of pick it up. Vectors in the plane. We're on practice 3B, and we've just gone over the first one, I think, and we're gonna go from there. All right. All right. Okay. So I had asked you to kind of finish this one up, this practice 3B. So let's see how you did. All right. All right. So Shandon, what do you have for U minus V?
-2, 1.
-2, 1. Excellent. Any questions on that? All right. For the next one. Jordan. 2U minus 3V. What do you have for that?
-7 and 1.
-7 and 1. Good. Any questions on that one?
Yeah, could you just do a quick run through?
Sure. You bet. So 2U, so you do 2 times, okay, so vector U is 1, 2. Minus, and then 3V, so 3 times vector V is 3, 1. So when you have a scalar times a vector, you just distribute and multiply through. So you get 2, 4 minus 9, 3. And now when you're adding and subtracting vectors, you add and subtract each of the components. So you add the x components, or subtract in this case, so 2 minus 9, and then you subtract the y components, 4 minus 3. And so 2 minus 9 gives you -7, 4 minus 3 gives you 1. All right? Okay, and the last one. Taylor. So 5u plus 4v.
17, 14.
17, 14. Excellent. Okay. Anybody want me to go through that one? Okay. All right. Oh, let's need a copy of that. Okay, so now the next thing is to find unit vectors. Okay, and so I know you did this. So to find a unit vector u that has the same direction as a given non-zero vector v, you divide the vector by its magnitude. So this is the vector in component form. You divide it by the magnitude. So in this case, the vector u is called a unit vector in the direction of v. All right. So first, we're going to find the magnitude then. Okay. Let's see. Is this it? No. Let's just go ahead and do practice 3C. Okay. So the first thing we're going to do is find the magnitude, and then I'm going to have you divide by it. So for practice 3C, first find the magnitude. Of vector v. All right, so Jordan, what's the magnitude of this vector?
Is it 1?
No, the vector v, not the unit vector. All unit vectors have a magnitude of 1. So the vector we're going to create has a magnitude of 1. But this vector does not have a magnitude of 1. Do you remember how to find the magnitude? You take and you square each number, add them up, and take the square root. So you say 7 squared plus negative 3 squared. So that's going to be 49 plus 9, which is this. So the square root of 58 is the magnitude of the vector. Okay. And so now to get the unit vector, what you do is divide this vector v by that magnitude. And so your answer is going to be, so you take the 7 and divide by radical 58, comma, negative 3 divided by radical 58. So you take the original vector and divide by the magnitude. And so I call that u sub v, which just means to me it's the unit vector in the direction of v. Now, if I were writing a book, I would only use u for a unit vector. But your book just use it for any vector. And that's annoying to me, because I just like it as a unit vector. All right, so now what I'm going to do now is take the magnitude of this to just prove to you that it is a unit vector, which means it has a magnitude of 1. So to calculate the magnitude of this green vector. We take and we square each thing, each component. So 7 over radical 58 squared plus negative 3 over radical 58 squared. So this would be how you would like check your work on the test to see if you really got this question right. So when you square this out, you get 49 over 58 plus 9 over 58. And then when you add those two together, you get 58 over 58, which is 1. So that's how you check to see if you really do have a unit vector. Okay? All right, let's do another one, just for fun. So this one is not going to be on your guided notes, so you could just, but I want you to do this. Okay, so I want you to find the unit vector in the direction of v. All right, so Dominic, what do you have?
I got 2 over square root of 53 and 7 over square root of 53.
That's it. Great job. Any questions on that? Okay, so now I'm gonna, the next thing is what's called a linear combination. Okay, now I'm gonna give you some notes, and it sounds way more complicated than it is. But to write a linear combination of a vector, what you do is you just drop the component brackets, and then you just put an I with the first component plus, and then you would put a J with the second component. So that's it. This is a linear combination of this vector in component form. Okay? So now I'm going to teach it a little bit more detailed here. Okay, so let V be a vector v1, v sub 1, comma, v sub 2. Then the standard unit vectors that can be used to represent V as V. So you put an I with the first component and a J with the second component. Where the scalar V1 sub 1 is called the horizontal vector. And the scalar V2 is called the vertical vector. And putting them together is called making it a linear combination. Okay, so what the i's and j's are is those are actually what we call standard unit vectors. So the I is a vector that goes horizontally 1 unit. The j is the vertical vector that goes vertically 1 unit. So what we're doing is breaking it down to these standard unit vectors is what it's called. So again, if you have the vector and component form 3, 5, then the linear combination of the standard unit vectors would just be 3i plus 5j. So you drop the brackets and you put a plus in the middle. Okay, so here we have a vector. So I give you the initial point and the terminal point. So the first thing you need to do is write this vector in component form, okay, with the funky brackets. Then I want you to rewrite it as the linear combination of the i's and j's, okay? So see if you can do that. All right, so Taylor, what's the component form of this vector?
Negative 10i plus 9j.
What was the first one?
Negative 10i.
So no. So let's talk about how we put the vector in component form, okay? When you have the initial point and the terminal point, you always do the terminal minus the initial, okay? So it's terminal minus the initial point. Okay, you can look over yesterday's notes. So here, we would take -8 minus -2, and then 3 minus 6. So then -8 minus a -2, add the opposite, and that's -6. 3 minus 6 is -3. So that's the vector in component form. All right, so Shandon, what would be the linear combination of this vector?
Negative 6i subtract 3j.
Subtract 3j. That's right. Okay. All right. Any questions on that? Okay, so now if we need to work with the components of a vector, we can write it as a linear combination or component form. Or in the next example, I'm going to use the trig form. So that's the magnitude of the vector times the cosine of the angle, comma, the sine of the angle. So all of these forms we can use interchangeably. So, but like in physics, where we take a vector and we're going to break it down to like the horizontal and vertical components, it's best to use the trig form, because then when we add and subtract vectors, well, you'll see. Okay. So, for example, in this one, so it says a baseball is hit and leaves the bat at a speed of 100 miles per hour at an angle of 20 degrees. So the speed of the bat, that's the velocity. That's the magnitude of the vector. All right, and then the angle we put in for the theta. So if it's 20 degrees, we can do it as 20 degrees. I mean, we don't have to convert it to radians or anything. So then to get this and write it as a vector, all we need to do is just put in the calculator 100 times the cosine of 20 and get that. And then we do 100 times the sine of 20 and get that. So you just got to make sure you're in degree mode. Okay? All right.
So when you get that V, doesn't that mean like magnitude? So you have to have the
Yes.
direction as well as the miles per hour?
No,
Or does
no,
it-
just the miles per hour is the magnitude.
Okay.
So remember, the vector has magnitude and direction. So the magnitude is the 100 miles per hour, the absolute value of it. So we're not worrying about whether it's positive and negative, going up or down or anything like that. Okay? Because
Okay.
the direction is going to be included in the angle. Okay? All right, so see if you can do practice 3E. So it's just a calculator, just punching it in the calculator, basically. All right, so Cameron, what do you have?
I got negative 70.711 and negative 70.711 again.
Yeah, excellent. And why is it the same?
Because it's 45 degrees is the
And at
reference.
45 degrees,
The sine and cosine are 2 radical 2.
yeah, they're the same. So you should get the same answer for each one. Okay, great. Any questions on that? Okay, so now Mr. Fritz told me you were having a little bit of trouble with the physics application. And so I'm going to go over that again. Basically, in this next example, we're going to have like a plane that's being pushed off course by the wind. And if you're a navigator, so you've got to be able to allow for that. You've got to account for that. Otherwise, you're going to be off course. So what we do is, just like this, we will write the velocity of the plane as a vector. Okay? And then we'll do the same thing with the wind. And then we'll add them up. Okay? All right. So to find the resultant vector of the plane and the wind, you put each in component form and then add. Now, there is one little tricky part though. And that is with the angle. Okay. So here it says an airplane has an airspeed of 724 kilometers per hour. So that's the magnitude. That's its magnitude. At a bearing of north 30 degrees east. Okay, so this is the tricky part, is that sometimes the angles for navigation are given like north, east, or like a compass heading, which straight up is due north. Well, neither of those is what we do use in trig. So here, for example, if it's north 30 degrees east, that's this angle right here. Okay? But see, in trig, we measure up from the x-axis. So to convert this angle to a trig angle, it's 60 degrees. Okay? So to find the component form of the plane, then we're going to put in the calculator 724 cosine 60 and then 724 sine 60. So why don't you go ahead and do that? All right, so Andrew, what do you have?
362, 627.0027.
So the 362 is exact, or is there a decimal part of that?
I didn't get one.
Okay.
It's exact.
So 362, and please tell me the second part again.
627. Point
And
zero
this-
zero
0.0027.
27.
So I'll just put 0.003. Okay. So everybody okay with that? Okay. So now let's look at. So that's the plane. So now we need the vector for the wind. It says that if the wind velocity is 32 kph from the west, okay, so that's all we need. So the magnitude of the wind is 32. What's the angle?
180.
180. Okay. So 180. Okay. So now put that in your calculator and get that. Oh, wait. Okay, hold on. I just realized something. The way the English is actually messing us up here. Is it saying that the wind is blowing west? No, it's saying that the wind is from the west. So if the wind is coming from the west, which way is it blowing? East. Okay? So that's a pretty subtle. So we actually got this wrong here. It's not 180. If it's blowing east, then what angle is it? What's the trig angle? If it's blowing east. 0. Okay? So that's what you put in there. because it's from the west. From the west, so that means it's blowing east. So that's very tricky. All right, so Brooke, what do you have?
32-0.
32-0. Okay, so that's the vector of the wind. Okay, so now to put them together, how the wind is affecting the plane, what we do is we add these two vectors together. Okay, so we're going to add these two together. So I'm going to call that P plus W. All right, so that would be what, 394? 627.003. So that vector represents the plane with the wind. Okay, just adding those two vectors together. So then with the plane being pushed by the wind, how fast is the plane going? How could I figure that out? How could I find the true speed of the plane?
You do the square root of 394 plus the square root of the second vector.
So
you
what
find
is
the
that
hypotenuse type of thing.
So what is that called, what I'm finding? Wait,
The magnitude.
The magnitude. So we just find the magnitude of this vector P plus W. Okay? So why don't you go ahead and do that? So it's the square root of each of those squared. All right, so Cameron, when you've got it.
740.52.
And the units are going to be kilometers per hour. Okay, so the airspeed on the we said it was originally going 724, but it's actually not, because the wind is pushing it and making it go faster. So it's actually going faster than what you might see on the dial there. Okay. All right, now, what about its true direction? How do we find the direction that it's going? Because the wind is blowing it off course, I need to account for that.
Find the unit vector.
Actually, that could do it, but there's an easier way.
Would you do inverse tan of 394 over 627.003?
Yeah, except it's the B over the A.
Oh, okay.
The second one over the first one. Okay, so to find the direction of the vector, we did the inverse tangent of B over A. So that's what we want here. So let's do the direction. So theta prime is the inverse tangent of B over A. So that's going to be the 627.003 over the A, which is 394. So, when somebody has that, just let me know.
It's 57.86. And would it be north of east still?
Yeah, 57. Well, that's the trig angle.
0.86.
So 57 point what? 486?
No,
Oh,
just
8.
86.
Just 86. And that's degrees. Okay, so now that's in quadrant 1. And so we're in quadrant 1. So that's the right one. And so basically, remember, we said that the plane was going at an angle of 60 degrees. But see, the wind is blowing to the east. And so the plane is actually going at 57 degrees. Now, and so if you wanted to convert it back to the navigational angle, then you could say, let's see, that would be north 32.14 degrees east. But I like the 57.86 answer just fine. But, you know, these crazy pilots, they have their own way of doing angles, I guess. Okay?
So did you get the 32.14? Did you just subtract it from 90 and then just say?
Yeah, so if this is my trig angle coming up here, then it would be, so this is north, and so you do north, and then you subtract this angle from 90, and then east. Okay? So, yep, that's exactly what you do. Okay? All right, any other questions on that? I hope that's a little more clear. So like in physics, you'll have an object and you'll like draw all the forces that are on it. So like maybe like gravity, the wind, you could have pulling it with a rope, or, two kids pulling it with a rope, and have those forces. And then what you do is you can add all those vectors together and then do a horizontal and vertical components of all of the vectors and then add them up. So you add up all the vertical forces, add up all the horizontal forces, and then that tells you which way it's going to be going and so on. Okay. So I mean, they can get a little more complicated than that, but really that's, if you can do this plane and wind, you'll be able to do and that's the hard part of physics, I think, is dealing with those vectors. So, okay. All right. Well, so that's 8.5. Whoops. And so now we want to go to 8.6, the dot product and its uses. And now this is a short lesson to begin with, and Mr. Fritz said he pretty much covered it all, but I just want to go through it really quickly just to make sure. It is only, the guided notes are just one page on this, so this is a shorter lesson to begin with. Now, one of the things that I'm not going to do that is in the book is they talk about projections of vectors. We're not going to do that. Okay? All right, so the dot product is kind of a way to multiply vectors together. There's several ways that you can do it, but one is called a dot product, and the dot product is where you take, so u dot v is you multiply the first numbers together, and you multiply the second numbers together, and then you add those up. Okay? And it says this product yields a scalar rather than a vector. So a scalar is like a number. So when you do a dot product, that's important that you know that your answer is going to be a number, not another vector. Okay? All right, so let's see. 3, 4. Okay, so let's try this one. See if you can do this dot product here. See if you kind of remember. All right, so Ellie, when you've got it.
-6.
Yes, because see what you do is you take the 3 times the 2 and 4 times -3. So that 6 plus -12 is -6. All right. Any questions on that? All right, go ahead and do the other two. All right, Ellie, I guess you get all the easy problems today.
46.
46 is correct. Good job. Any questions on that one? Okay. Let's see. 4, 4, 5, 2, 3. All right, Ellie, take us home. What's this last one?
23.
23. Okay. So again, the answer is a number, not a vector. Okay. All right. Actually, no. Okay. All right. So then the properties here. You probably went over these. U dot V is equal to V dot U. So the order doesn't matter. 0 dot any vector is 0. Okay, and then you can distribute with the dot product. So U dot V plus W is U dot V plus U dot W. And you can also distribute a scalar. So if you have a scalar times a dot product, you can do the dot product first, or you can distribute the scalar through and then do the dot product. But the one that I have highlighted here is that U dot U, a vector dot itself, is equal to the magnitude of the vector squared. Okay, let's see, do I have that? Okay, so the dot product of a vector with itself is the magnitude squared. And so if you already know the dot product, that's kind of an easy way to think about it. Because what are you doing? You're multiplying, you're squaring and adding up, just like when you're calculating the magnitude. But there's no square root. All right? So see if you can do practice 1B. Use the dot product to find the length of U. So In other words, find the magnitude. All right, so Shannon, when you've got it.
Fifteen. I got 15.
I'm sorry, what'd you say?
I got 15.
15? Okay. So you take and you dot it with itself. So you get -9 squared plus 12 squared is 225. So that's the magnitude squared. So then to get the magnitude, you take the square root of that. And so you get to square root of 225 is 15. So great job. All right. So a vector dot itself, so here that's 225, and that's the same thing as the magnitude squared. Okay. All right, any questions on that?
Could you uncover it, please?
Oh,
And
sure.
Can you scroll down a little? Yeah, thank you.
So you just find the magnitude for it then?
Yep.
Okay.
So to find the length, that's the same thing as finding the magnitude. Okay.
So what does it mean when it says the magnitude squared?
Okay, so you see, our answer is 15. So if I square that, I get 225, which is what the dot product was.
Oh, okay.
So the dot product is the magnitude squared. The dot product with itself. A vector's dot product with itself. Okay? All right, other questions on that? Okay. No, that's not. We want the angle. Okay, so this is the big application of dot products, is to find the angle between two vectors. Okay, so if theta is the angle between two non-zero vectors, then the cosine of the angle is equal to their dot product divided by their magnitudes. All right? So see if you can do practice 1C using this formula. So you're trying to find the angle between the vectors. All right, so Junior, what's the dot product of these two? So what's U dot V?
Zero.
0. All right, what's the magnitude of U?
3.
And what's the magnitude of V?
6.
6. So when we make that fraction, it's going to be 0. Let's see here. What just happened? No. Okay, so we're going to get 0 over. Come on. Sorry. So we're going to get 0 over like 18, which is 0. Okay? So then you say, well, what angle has a cosine of 0? You don't even need to put that in your calculator. That one's going to be 90 degrees. I mean, you could do inverse cosine of 0, but hopefully you know that one. So that's the answer. Okay. Now, with vectors, if they form a 90-degree angle, okay, then we call those vectors orthogonal. If they form a 90-degree angle like this one, okay? So if they form a 90-degree angle, they're orthogonal. So the last problem on the sheet says, are the vectors, and they give you two vectors, orthogonal, parallel, or neither? Well, it turns out that since their dot product here was 0, then they formed a 90-degree angle, so they were orthogonal. So to test to see if two vectors are orthogonal or perpendicular, all you have to do is just check and see if their dot product is 0. Then they will make a 90-degree angle. If they're parallel, then one will be a multiple of the other. So like you multiply by 2 or 5 or anything. And then if neither of those things happen, then it's neither. Okay? So for Thursday, I just want you to answer that question, practice 1D. And so we'll start off going over that, and then we're actually